Welcome to this explainer. If you're ready to take your very first steps into coding, you are in exactly the right place. Today, we aren't going to get bogged down in commas, brackets, or the specific rules of any one language. Instead, we're focusing on the foundational mindsets that all software developers use to translate human ideas into computer logic.
So, let's just dive right into it, because honestly, this is the most important question a beginner can ask. Before you worry about syntax or which programming language to install, you have to decide how you actually want to attack the problem at hand. Think of it like deciding whether to build a house using wood, brick, or steel. The material you choose completely changes how you approach the construction, right?
Well, in the software world, those different materials are called programming paradigms. A paradigm is basically just a fundamental style or approach to programming. Think of it as a highly specific tool in a developer's toolkit. Different paradigms give you entirely distinct ways of organizing your code, structuring your data, and communicating what you want to the computer.
To give you the ultimate beginner's toolkit, we're going to quickly explore 5 key areas today: imperative and procedural, object-oriented, functional, declarative, and finally, how to choose the right tool for the job.
Let's kick things off with Section 1, Imperative and Procedural Programming, which focuses on step-by-step commands.
This is arguably the most straightforward approach out there, and it perfectly mirrors how you might follow a baking recipe in your own kitchen. You are telling the computer exactly what to do step by step. Just like a recipe tells you to first preheat the oven, then mix the flour, and then add the eggs, imperative coding lays out the exact sequence. As you can see, we start at 0, we count from 1 to 5, and we add each number to our total. Look at this little snippet of Python code. You aren't leaving anything up to interpretation here. You are explicitly commanding the computer, hey, loop through this range of numbers and manually update my total every single time. It's incredibly direct. Now, closely tied to this is procedural programming. Think of it as a really helpful subtype of that imperative mindset. Procedural programming simply takes those step-by-step commands and groups them together into specific named tasks or routines. So instead of writing out the exact recipe for a cake every single time someone orders one, you just create a reusable procedure called bake cake. You can easily reuse it over and over, kind of like calling a single greet function for Alice, then Bob, without rewriting the underlying instructions.
But there's a really fascinating trade-off here. Imperative and procedural code is wonderfully simple and gives you total direct control. But that simplicity becomes a huge disadvantage when your program grows massive. Imagine trying to explicitly track every single ingredient, temperature, and stirring motion for a gigantic commercial bakery producing 10,000 distinct pastries a day. The manual tracking becomes a tangled, error-prone mess.
Which brings us right to Section 2, Object-Oriented Programming, or real-world modeling.
To solve that massive scalability problem we just talked about, Object-Oriented Programming, or OOP for short, packages everything into neat, self-contained little boxes called objects. It essentially mimics the physical world around us. Think about it. In the real world, you don't look at a dog as a sequence of biological commands. You think of a dog as an entity that has data, like its name and breed, and behaviors, like barking and running. OOP wraps that data and behavior together.
For example, if you're building a racing game, you'd build a car object. It holds its own data, known as attributes, like the make, model, and year. And it holds its own functions, known as methods, like starting the engine. So you just create a specific instance of that car, say a 2020 Toyota Corolla, and tell it to start. This emphasizes a core concept called encapsulation, basically keeping everything related to the car safely insulated inside the car object itself.
Because of this, OOP is absolutely incredible for building large, scalable systems. If your game needs thousands of cars, animals, and buildings interacting, OOP is your best friend. But you have to watch out because it can add completely unnecessary complexity to a simple app. I mean, you wouldn't build an entire automobile factory object just to calculate your grocery bill, right? It can be total overkill.
Next up is Section 3, Functional Programming, which relies on pure math evaluation. So what if we remove the idea of changing state entirely and just treated our code like pure mathematics? Well, in functional programming, we don't alter the original data at all. There's a strict avoidance of mutable data. Think of it like a perfectly clean factory assembly line. You pass raw materials into a machine and a brand new product comes out the other side. The machine didn't destroy or change your original blueprint, it just evaluated the inputs and created something entirely new.
This heavily relies on what we call pure functions. A pure function guarantees that if you give it the exact same inputs, it will always produce the exact same outputs,
with absolutely zero side effects anywhere else in your program. For instance, if you pass a list of numbers into a functional square process, it returns a brand new list of squared numbers. It never modifies the original list. That original list stays completely safe and untouched. Now, because of this pure approach, the lack of shared mutable state makes this paradigm amazing for running code in parallel. You can literally have multiple processors working at the exact same time because they aren't accidentally overwriting each other's data. That said, the abstract, heavily mathematical nature of it can definitely mean a steeper learning curve for beginners who are more used to step-by-step logic.
Moving to Section 4, Declarative Programming, where we focus entirely on the goal. This fourth toolkit item completely flips the script on how we communicate with our computers. Imperative programming focuses on exactly how to achieve a task. Declarative programming focuses on what to achieve, completely ignoring the how. Think of it like ordering at a nice restaurant. You tell the waiter what you want to eat, say a medium-rare steak. You are declaring your goal. You do not march into the kitchen and tell the chef how to turn on the stove or exactly how to season the meat. You just declare the result you want and let the system figure out the rest.
This is incredibly common when dealing with databases. In this Python database query right here, you're simply declaring the desired outcome. You want to select users where their age is greater than 30. Notice how you aren't providing any underlying procedure for how to search the database, how to index the files, or how to sort the rows. The underlying system handles all of that heavy lifting for you. Because of this, declarative code has extremely high clarity and readability. It is wonderfully easy to maintain. However, you do surrender a lot of fine-grained control over how the execution actually happens behind the scenes. If the chef in the underlying system isn't very efficient, well, your program might run slower, and you can't just dive into the kitchen to optimize the exact steps yourself.
And that brings us to our final section, choosing the right tool for the job.
We've looked at the step-by-step imperative recipe, the real-world modeling of objects, the mathematical purity of functional assembly lines, and the goal-oriented declarative restaurant order. The absolute biggest takeaway from this explainer is that there is no single perfect paradigm. They are all simply lenses that guide how you think about logic. The best programmers in the world don't rigidly stick to just one style. They have a massive toolkit, and they know exactly when to pull each of these tools out depending on the specific problem they're trying to solve.
You now have the foundational map to start your coding journey. You understand the language of logic that goes far beyond just typing words on a screen, which is huge. But the real, exciting question left to answer is this. Now that you know the mindsets behind the code, which approach will you use to write your very first program? Dive in, experiment with these different tools, and most importantly, have fun building.